Now it is time to talk about trigonometric functions. Here is a textbook definition of what a trigonometric function is. I will leave it here for you to read. And below are the 6 main trigonometric functions. Now, don't worry too much. We won't go in depth in all of these functions. Maybe in the future we will have more advanced lessons and we will talk about them in more detail. For now, the only 2 functions that we will concern ourselves with are sine and cosine. Now, if you remember your high school lessons, the sine of an angle is equal to the opposite side of a right triangle divided by its hypotenuse. And the cosine of an angle is equal to the adjacent side of a right triangle divided by its hypotenuse. Now, let's see this in a very practical way and in a visual way so we can understand it better, and mainly so we can understand how this is important for us within our work with 3D geometry. Here we are back in Houdini, and I have drawn in the viewport what's called a unit circle. A unit circle is a circle with exactly 1 in diameter, in this case 1 meter in diameter, and it's particularly useful when explaining the sine and cosine functions. I will also display a line that I have created, parting from the origin and touching the radius of the circle. And if you think about it, no matter what angle this line is at, it will always have 1 unit in length. I have also animated this line so it rotates based on the frames of my animation. So you'll notice how it will rotate 1 degree for each frame of the animation. So I will open the animation settings, and you will notice how my animation starts at frame 0 and ends at frame 360. So if we were to play the animation right now, the line would do a full circle. So for now, let's leave it at 30 degrees. And I will also display a line representing an opposite side of a right triangle, as well as a line representing the adjacent side. So here are my 3 lines forming a triangle. Now let's go back to the definition of our trigonometric functions for a moment. And let's just remember that the sine of an angle is the opposite side of a triangle divided by the hypotenuse. Now it should be much clearer for us to see here with this example, and let's write it down here. The sine of the angle, in this case this angle that we could call theta, is equal to the opposite side divided by the hypotenuse, which in this case, if you remember, our hypotenuse has a value of 1. The length of this yellow line is 1. So the opposite side divided by 1, this would be cancelled, and we would only have the opposite side as a resulting sine value. Now, since we're working on an x and y coordinate system, our opposite side would be equal to a y coordinate. Now let's take a look at the cosine. So the definition of the cosine function is the cosine of an angle equals the adjacent side of the triangle divided by the hypotenuse. So let's write it down here. So remember, our angle is theta here. The cosine of our angle is equal the adjacent side divided by the hypotenuse. Again, our hypotenuse, this yellow line, right now has a value of 1. And any number divided by 1 will result in this a number. So we will cancel this. And the result would be the adjacent side of the triangle. And again, since we're working on an x and y coordinate, very conveniently, this adjacent side is equal to our x value within the grid. So by now you must be wondering, how is all this information relevant for us as 3D artists? And the answer is, with the trigonometric functions, we can map the position of any object within a circle or within a curved path. So let's display what we just found out. The sine will be equal to our y coordinate in the 3D space, and the cosine will be equal to the x position in the grid. So let me display a small sphere that I created, and I will play the animation, and you will notice how the sphere is following the circular pattern of the unit circle. Now let's see how this was done within the geometry node. I will dive into the node and select the sphere. Actually, I will recreate the exercise for you to understand how I did it. I will create a new sphere. I will make it much smaller. And I will connect a transform node below to be able to recreate this animation. So right now, if I play the animation, I will only have the static sphere. And for now, let me turn off our triangle. Go back to the sphere. And in the transform node, I will create a very small function here. In the x position, I will type cosine, open parentheses, and as a variable, I will use the frame number, close parentheses, and type enter. Now notice how the sphere already moved. If I go back to my frame 0, the value of x will be 1. As I move towards the 90 degrees angle, the cosine reaches a value of 0 and starts getting into the negative values until it reaches -1 in 180 degrees. Now, all these functions are cyclical. Once they end, they will start repeating. For example, if we continue to the 270 degrees, the cosine value will again be 0, and again into the positive values till it reaches 1 in 360 degrees. So let's try doing something similar with the y position. Remember, the y position will be equivalent to our sine function. So I will type sine, open parentheses, and type our frame variable, which is $f, close parentheses, and control enter. Now, if we play the animation, you'll notice how the sphere is following the circular pattern that we drew. Now I will show you how we can replicate this motion using Vex in a point wrangler. So here to the side, I will create a point wrangler and connect it to the sphere. Notice how the sphere is a primitive object, so it only has one single point. And I will make visible the point wrangler. And I will type the following code. V at P, so we know this, P is the position, dot X would be the position on the X axis, equals the cosine, open parentheses, and type my frame variable, which is at frame, close parentheses, and semicolon. Now, if we evaluate the code and press play, you will notice something different. Notice how the ball goes left to right in a much quicker way. So here's a small gotcha when you're using the sine and cosine functions within Vex. These functions are expecting a value in radians, and we're used to thinking in terms of degrees, but this is very easily corrected using another function called radians that will convert this value from radians to degrees. So now if we press play, the animation should work as expected. Now let's take care of the Y position. So press enter and then type V at P dot Y equals sine, or SIN, open parentheses, radians, open parentheses, at frame, close parentheses, semicolon. Now if we evaluate and press play, we will have the exact same result that we have with our transform node.